Drop a piece of glowing hot metal into a bucket of ice water, and you know exactly what happens. The water boils, the metal cools down. But how do we measure the exact amount of energy moving between them? To do that, we rely on the first law of thermodynamics. This law states that energy cannot be created or destroyed. It can only transfer from one place to another or change forms. Next is the second law, which deals with entropy, or disorder. Take a look at this diagram showing states of matter. As energy disperses, natural systems tend to move from an ordered solid state into a liquid and finally into a highly disordered gas. Entropy naturally increases. Because energy obeys these physical rules, we can mathematically track it. We can predict exactly how heat will move and disperse in any chemical reaction. Heat moves through three specific pathways: conduction, which requires physical touch; convection, which operates through fluid currents; and radiation, via electromagnetic waves. This diagram shows a pot of boiling water over a campfire, illustrating all three pathways operating at once. Conduction heats the physical handle you touch. Convection rolls the boiling water inside the pot. And radiation is the heat you feel on your face when standing near the fire. Whether it travels through physical contact or empty space, heat always flows from a hotter object to a colder object until the system reaches a balance. Look at this potential energy graph showing an endothermic reaction. In an endothermic process, the system absorbs heat, cooling the surroundings, and the products step up to a higher potential energy level than the reactants. In an exothermic reaction, the system releases heat, warming the surroundings, and the products end up at a lower energy level. Notice the two distinct vertical arrows here. The arrow running from reactants to the peak is activation energy, the initial hurdle to start the reaction. The vertical difference between reactants and products is the net enthalpy, or heat of reaction. This heating curve for water tracks temperature changes over time. The sloped lines show where the water's temperature is actively rising. The flat plateaus represent phase changes, where added energy is used entirely to break bonds. Now look at this phase diagram for water, plotting pressure against temperature. Point A is the triple point, where solid, liquid, and gas coexist in equilibrium. Way up at point E is the critical point, where liquid and gas states become indistinguishable. By mastering how to read these graphs, you can determine if a system is absorbing or releasing energy with a single glance at its overall shape. To calculate the exact enthalpy change, we use a standard formula. This equation shows that the heat of reaction equals the sum of the enthalpy of the products minus the sum of the reactants. We find these values using a standard heat of formation reference table. Every compound has a specific baseline energy value recorded here in kilojoules per mole. When running these calculations, watch out for two common errors. First, notice that elements in their standard state, like solid aluminum and iron, have an enthalpy of exactly 0. And for the compounds, you must multiply their table values by their stoichiometric coefficients, the 2's in the balanced equation. With this math, chemists calculate the exact energy output of a reaction without ever having to light a match or run the physical experiment. Step outside barefoot on a summer day. The concrete pool deck burns your feet, but the pool water feels cool. This happens because water has a much higher specific heat capacity than concrete, meaning it requires significantly more energy to raise its temperature. We calculate this using the heat equation shown here. Q equals mc delta T. Q is the heat energy in joules, m is the mass in grams, C is the specific heat capacity, and delta T is the change in temperature, always calculated as final temperature minus initial temperature. Let's put this into practice. Pause the video here and try to solve this problem involving a heated piece of cadmium metal. Find the initial temperature. Here is the algebraic solution. We plug the 134 joules in for Q, the 15 grams in for M, and the cadmium specific heat in for C. By dividing out the mass and specific heat, we isolate the change in temperature. Subtracting the final temperature of 62.7 degrees gives us an initial temperature of 24.0 degrees Celsius. Knowing the specific heat allows us to quantify exactly how stubbornly different materials resist changing their temperature. This diagram shows a calorimeter, an isolated device used to measure energy transfers. Inside a calorimeter, the first law of thermodynamics is absolute. The heat lost by the hot metal system is perfectly absorbed by the surrounding water. Because the energy balances perfectly, we can set two heat equations equal to each other, forming the equation shown at the top. Mass times specific heat times delta T of the metal equals negative mass times specific heat times delta T of the water. Let's apply this to the 2.50 gram zinc sample problem. We plug the water's variables into the left side of the equation and the zinc's variables into the right. The most common algebra mistake happens here. You must distribute the negative sign on the lost side across the entire delta T bracket. Doing this correctly flips the signs, allowing us to isolate the initial temperature and land cleanly on 719 degrees Celsius. This review graphic covers the critical elements you'll need. On the left, we have the rules for exothermic and endothermic processes. On the right, your key formulas, alongside the specific heat of water, and a reminder on how to properly calculate temperature change. Take a screenshot of this frame right now to use for your final review. With these rules memorized and careful execution of the algebra, you have to